Hello, Hello everyone. I'm Alka Jangid from IIT Kanpur. I'm TA for Nature and Properties of Materials, and today for week 5 we'll be studying about composite materials. So this course is offered by Professor Vishal Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. Now firstly we'll be going through some sample assignment questions. So first question is reinforced polymer composite is made by the incorporation of. Your options are elastomers into the polymer, fibers into the polymer, or plasticizers into the polymer, or gaseous additives into the polymer. So the answer will be fibers into the polymer. So we know that except fibers, other options such as elastomers, plasticizers, and gaseous additives, these don't have higher elastic modulus, so they won't be providing high stiffness to the composite. So we can explain it by saying that fiber reinforced polymer FRP, also fiber reinforced plastic, is a composite material made of a polymer matrix reinforced with fibers. So the fibers are usually glass, carbon, or aramid, although other fibers such as paper or wood or asbestos have been sometimes used. The polymer is usually an epoxy or polyester thermosetting plastic, and phenol formaldehyde resin are still in use. So FRPs are commonly used in the aerospace, automotive, marine, and construction industries. And polymers can also be reinforced with particles of higher Young's modulus. So these can be either particles or fibers for making these reinforced polymer composites. Now the second question is aluminium alloys for automobile parts are reinforced to increase. Options are strength, wear resistance, elastic modulus, or density. So your answer will be wear resistance. Now in case of aluminium alloys, ceramics are reinforced to improve their wear resistance. One of the applications is the engine block of automobiles, which require wear resistance. So mainly alumina is reinforced inside aluminium, because aluminium alloys they are soft, so they wear easily. Now third question is find the odd combination out of the following composite applications. Your options are CFRP Dreamliner, GFRP in storage container, aramid in bridge reinforcement, or CMC in brake disc. And your answer will be aramid in bridge reinforcement. Now we can explain this by saying that aramid fiber reinforced polymer rebars are being used as internal reinforcements of concrete structures for more than 10 years. Aramid fibers, short for aromatic polyamide, are a class of heat resistant and strong synthetic fibers. Other composites consist of reinforcement, either ceramic or glass in a polymer matrix, while aramid is polymer fiber used for reinforcement in ceramic concrete. Now fourth question is in Hall-Page model, hardness increases with a reduction in grain size. so in the Hall page model, hardness increases with a reduction in grain size because grain boundaries. Your options are that grain boundaries act as a source of dislocations, or grain boundaries add dislocation motion, or act as barrier to dislocation motion, or they act as sinks for dislocations. So your answer will be C. So it acts as a barrier to dislocation motion. Now explanation is a fine grain material, one that has small grains, is harder and stronger than a coarse grained due to a greater total grain boundary area to restrict dislocation motion. Now grain boundaries also act as a source and sinks of dislocations, but that is not the reason for hardness enhancement in metals. Now here it is a polycrystalline material, so here different grains are there, so all grains will have a different orientation. So when a dislocation is moving in this grain along particular plane, slip plane, so for moving that dislocation into another grain, it will require extra stress. So that's why these grain boundaries, they will enhance the strength of the material. Now question number 5. So the name of the process by which two or more chemically different monomers are polymerized to form a cross-linked polymer together with a byproduct such as water or ammonia. Your options are this process is either addition polymerization or copolymerization, linear polymerization, or condensation polymerization. Your answer will be condensation polymerization. Now we can explain this by saying that in case of condensation polymerization, it is a form of step growth polymerization where smaller molecules or monomers react with each other to form larger structural units, usually polymers, while releasing byproducts such as water or methanol molecule. The byproducts are normally referred to as condensate. So this H2O, ammonia, methanol, these all molecules that are forming, they are known as condensate. And another is addition polymerization. Now addition polymerization has it can be defined by the formation of addition polymers by the repeated addition of monomer molecules which possess triple or double bonds. And copolymerization is the formation of addition polymers which occur due to the addition of polymerization from two different monomers is called a copolymer. Now sixth question, which of the following is a disadvantage of using polymer composites in space robotics? Your options are low weight to strength ratio, susceptibility to temperature extremes, high cost of production, or limited availability of reinforcing fibers. And your answer will be B, susceptibility to temperature extremes. Now this can be explained by saying that polymers tend to creep easily and are not susceptible to temperature extremes. They show the advantage of a high strain to weight ratio due to low density. They also have low cost of production and good availability of reinforcing fibers. So this option is correct. Now question number 7. Which one is not the role of reinforcement in a composite? Your options are to enhance stiffness, to enhance strength, or to provide crack bridging, or to increase density? Answer will be to increase density. So this is not one of the role of reinforcement. Now composite is what? It is made of matrix and reinforcement. Now the reinforcement generally provides a composite with more strength, stiffness and toughness due to crack bridging. Now the main role of reinforcement is never to decrease density, but sometimes if we use ceramics in the metal matrix, it can reduce density to a very low extent. So this one is not correct, and other are the roles of reinforcement in a composite. So it will be enhancing stiffness, strength, and will be providing toughness due to crack bridging. Now question number 6. It's 8th, question number 8. So what type of material is often used in the creation of soft actuators in for soft robotics? Your options are shape memory alloys, carbon fiber, nylon or aluminium. So your answer will be shape memory alloys. Now we can explain this by saying that shape memory alloys work great as actuators for soft robotics, example nitinol. And shape memory alloys convert thermal energy into mechanical energy, making them desirable for making actuators. 9th question. Chain polymerization mechanism may occur due to, your options are cationic, anionic, only due to free radical and cationic mechanism, or all of the given options. So your answer will be all of the given options. So we can explain this by saying that free radical polymerization is a type of chain growth polymerization along with anionic, cationic and coordination polymerization. Now free radical polymerization is a polymerizing approach by which successive addition of free radicals takes place to form a polymer unit. Question number 10. Find the incorrect fact about the thermoplastics. Your options are they are soluble and fusible, they are generally linear polymers, and they are creep resistant, or they can be easily repaired. Your answer will be they are creep resistant. Now these are different type of, here they have cross linking, so these are the mainly thermosets, and these are linear and branched polymers, so these are thermoplastics. So in case of thermoplastics, they are prone to creep at higher temperatures. The creep resistance of thermoset polymers increases with the amount of cross linking between the chains, because cross linking is strong covalent bonding which doesn't let polymer deform. Now these are linear polymers and fusible because of it, and these can be repaired by simply heating. So these all statements are correct except they are creep resistant, because plastics, they creep very easily. Now I'll be going through some lecture slides, and firstly we'll be reading about composites. Okay, so composites, natural or artificial mixtures of two or more distinct phases or constituents, is known as composite. So mixtures may consist of either metals, polymers or ceramics. And primary engineering goal is to achieve a better balance of properties from the combination of materials. So this is a aeroplane, and these different colors, they all. So in aeroplane, these all different color, they are different composites. So red one is carbon or carbon and Nomex sandwich, and this carbon monolithic structure orange, and Kevlar Nomex sandwich, Kevlar Nomex sandwich with stiffening, carbon plies fiberglass Nomex sandwich. These all composites, they are used in making various parts of. Good afternoon. Okay, so now history. Now composites, they have history like from a lot, like 3000 before Christ. At that time also we see proof of use of these composites. So these type of bricks, like using simple mud and straw, they used to make these reinforced bricks. Now these straws, they will be providing some strength to it. And 100 before Christ, the steel composites, which were formed by repeated folding of a steel bar back on itself. And during Industrial Revolution, 1800 AD, concrete and cast iron is used. And now in modern composites, we from 1950 to present, we mainly use fiber reinforced composites. Now natural composites, so they exist throughout nature, and almost all natural materials are made of composites. For example, woods, bones, and various parts of trees, they all are made of using these composites. Okay, so in case some examples consist of wood. In case of wood, lignin matrix. So we know that composite are made of two parts, matrix and reinforcement. So matrix is made of lignin and hemicellulose wound in a spiral form. This wounds, they provide reinforcement to this composite. In case of bone, it is made of organic fibers, inorganic crystals, water, and fats. Such as these all, they combine make bones. So that's why bones, woods, these are these have very high strength. And 35% of bone consists of organic collagen, protein fibers with small rod-like hydroxyapatite crystals. Cast irons as composites. Now cast iron and steel, they both have, in case of cast iron we have graphite or cementite, and in case of steel we have cementite. So these both, they act as reinforcement. And in a metallic matrix will be of ferrite mainly. So both are composite like structures, so that's why they have very high strength. Classification of composites, so they are mainly of three types: particle reinforced, fiber reinforced, and structural composites. In case of particle reinforced, your reinforcement will be made of particles. So these can be either large particles or dispersion strengthened. In this case, particles will be nanometer size. Second is fiber reinforced, and third is structural. Structural will be of two types. These can be laminates, where different sheets with different orientation will be made into laminate structure. It can be a sandwich structure in which two different sheets will sandwich something, some forms like structure or honeycomb structure, which will provide it low density. Now, large particle composites. Example is concrete, in which is composed of cement. Cement, it will act as matrix, and sand and gravel that we mix in the form of particulates. Now the particulate phase is harder and stiffer than the matrix, and reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle. Now matrix transfers a fraction of the applied load to the particles, and improvement of mechanical behavior depends on strong bonding. Now reinforcing particles, they tend to restrain the movement of the matrix phase in the vicinity of each particle. Matrix transfers a fraction of the applied load to the particles, and the improvement of mechanical behavior depends on strong bonding at the matrix particle interface. Now concrete is made of using cement will be matrix, and then sand, stones and water, these all combine and they make concrete. It is example of a large particle composite. Now second type of composite is dispersion strengthened composites. Now particles are normally much smaller with diameters between 10 to 100 nanometer. Now strengthening occurs on the atomic or molecular level. Now matrix bears the major portion of an applied load, while the small dispersion particles hinder the motion of dislocations. Now this is what your small particles will look like. Thus plastic deformation is restricted. These dislocations, they provide plastic deformation, so such that yield and tensile strengths as well as hardness improves because of this restricted plastic deformation. Example is sintered alumina powder, flakes of aluminium coated with alumina, which are dispersed within an aluminium metal matrix. In this case, this light blue part is ceramic or some strong particle. So this particle has some surrounding stress field. So when this dislocation will move near to it, it will act as barrier and it will stop this dislocation from moving. So this will provide strength to the material. Here your particle size will be in this range, 10 to 100 nanometer. Now fiber reinforced composites for fiber phase. Now on the basis of diameter and character, fiber phase can be grouped into three types. It can be either whiskers, it can be either fibers, it can be wires. Now in case of whiskers, they are very thin single crystal that have an extremely large L upon D. L is your length, D is diameter. So this L by D ratio but have the form of fiber. And these are flow free and thus extremely high strength. So these won't be having dislocation, twins, that type of defects. So these are expensive also. because of their manufacturing. These include graphite, silicon carbide, silicon nitride, and aluminum oxide, etc. In case of fibers, a material that has at least L by D ratio equal to 10 is to 1. So 10, its length will be 10 times its diameter. Now it can be either polycrystalline or amorphous, and these fibers generally polymer and ceramics. Wires, they are relatively large diameters. Now they are made of typical materials include steel, molybdenum and tungsten. Now fiber reinforced composite matrix phase. So the role of matrix in a composite includes binding fibers together. It protects the individual fiber from damage by the external environment. So these fibers, they will be covered by this matrix. So this matrix will provide it. It will bear all the damage before fibers they get broken. Now it acts as a medium to transmit and distribute externally applied stress to fibers, and it serves as a barrier to crack propagation. Now requirements of composites. The matrix material should be ductile. Now all matrix, they are mainly, most of the times they are taken ductile compared to reinforcement. Elastic modulus of the fiber should be much higher than that of the matrix. Now there should be adequate bonding between the matrix and fibers. So there should be bonding at the surface of fibers. The role of fibers in composite include to enhance stiffness, to enhance strength, to provide crack bridging, and to enhance thermal resistance. Now the stress strain curve. So for the matrix, this blue curve is followed, and for the fibers, this red curve is followed. Now for blue curve, it has lower Young's modulus compared to this fibers. So for the matrix, it will fail in a ductile manner, and it has a lower strength, and for fiber it will fail in brittle manner, and it has higher strength. Now when we are making a composite using both of these, this stress strain curve for a composite will look like this. It will be intermediate to both of these. It will fail like this, and it will have higher Young's modulus compared to matrix but lower compared to fiber. Now volume and weight fractions. So if these fiber phases, these are dispersed in matrix like this, then these calculations will be followed. So if VF, VM, VV, VC, these all are volumes of fiber, matrix, void and composite. So total volume will be 1. These are volume fractions. So volume fraction we can get by simply dividing volume of fiber to the volume of composite. And for matrix also, volume of matrix divided by volume of composite. And for void, volume of void divided by volume of composite. Now volume of composite will be equal to volumes of fiber, matrix and voids. In case of weight, weight fraction will be similar to these, and total weight will be weight of composite equal to weight of fiber plus weight of matrix, and fractions will be equal to 1. by using this formula, like if we weight, we can write in terms of density, we can write density times volume. So we can get density of composite rho C equal to rho F VF, V is fraction, and rho M VM. Now longitudinal modulus. So when fiber direction is like this and we are applying load also in this direction, then this will be longitudinal modulus in this case. So the tensile load is acting along the fiber direction, and assuming perfect bonding between fibers and matrix. So if we are applying load in this direction, then fiber, matrix, they all will show similar strain. All matrix will go to a particular length. Now these all are equal, and now the tensile load PC applied on the composite lamina is shared by fiber and matrix. So PC will be equal to PF plus PM, and P load we can write in terms of stress times area. So rho C plus AC equal to sigma F AF plus sigma M AM. Now we can take AC to this side, and AC will be equal to AF AM. Now by using length will be similar, length will be equal. So finally we can get our elastic modulus will be equal to EF VF, V is fraction, plus EM VM. Now this is known as rule of mixture for composites. In case of transverse modulus, your fiber direction will be in this direction, and at 90 degree will be applying load. Now the tensile load is acting normally in the fiber direction. Now sigma F will be equal to sigma M equal to sigma C. The strain or deformation of the entire composite is EC equal to EF VF plus EM VM. Now this can be rewritten as Hooke's law as, now strain can be written as stress upon elastic modulus. So after writing this, we can simply say that all sigma is equal. So sigma will be cancelled from both sides. So 1 upon EC equal to VF upon EF plus VM upon EM. And EC, this Young's modulus of total composite, it can be obtained like this. Now metal matrix composites. So depending on type of matrix, there are 3 types of composites: metal matrix, ceramic matrix, and polymer matrix composites. Now in this case, MMC matrix will be ductile metal. It will have usually alloys of aluminium, magnesium, titanium, and copper. And in case of fiber, carbon, silicon carbide, boron, aluminium oxide, etc. Now advantages of PMC over PMC. So metal matrix composites have certain advantages compared to polymer matrix composites. These have higher operating temperature. Now polymers, we know that they can operate at lower temperatures only. And non-flammability, polymers are flammable also. And greater resistance to degradation by organic fluids. And demerit includes MMCs are costlier than PMCs. Polymers are cheaper. So metal matrix composites are costlier. Now properties of several metal matrix composites reinforced with continuous and aligned fibers. Now these are certain fibers: carbon, boron, silicon carbide, alumina, carbon, Borsig, these all, and metrics are these. So in these metrics, their longitudinal tensile modulus and longitudinal tensile strength are given, and their density is given. Applications of MMCs. So they are used in making tank armors, golf clubs, space shuttle frame, antenna, boom for the Hubble Space Telescope, which is made using graphite fibers in 6061 alloy of aluminium. Second is polymer matrix composites. Now these are, first is glass fiber reinforced polymer. So here we'll be reinforcing it with glass fibers. Matrix will be plastic, most often epoxy, polyester resin, and reinforcement is glass fiber, e-glass, and diameter will be 3 to 20 micrometer. Now this glass fiber is typically made using 55% of silica, 16% of calcium oxide, 15% of alumina, 10% of B2O3, 4% of magnesium oxide. Now it is easily drawn into high strength fibers from the molten state, but it has limitation that service temperature up to 200 degrees C, above which polymer, which is a matrix, will start deteriorating. Applications are in automotive and marine bodies, plastic pipes, storage containers, and industrial storage container and industrial flooring. Now these glass fiber reinforced composites, these have density of 2100 kg per meter cube, which is lightweight, and they have tensile modulus of 45 and 12 in longitudinal and transverse direction, and they have tensile strength of 1020 and 40 in longitudinal and transverse directions. Now another polymer matrix composite is carbon fiber reinforced polymer. In this case, your matrix will be polymer resin and fibers will be of carbon fiber. Now carbon is a high performance fiber material because these have highest specific modulus and specific strength of all reinforcing fiber materials, and they retain this strength at elevated temperatures. At room temperatures, they are not affected by moisture or a wide variety of solvents, acids, and bases. Fiber diameters are normally in the range of 4 to 10 micrometer, and their applications are carbon fiber wheel, Boeing 787 Dreamliner. Nearly 50% frame of this is made of CFRP, and mountain cycle, bicycle frame, seats, racket, etc. These all are made of CFRP. Now it has a density lower compared to glass fiber. So it has 1600 kg per meter cube. And this tensile modulus is 145 and 10 in longitudinal and transverse direction, and 1240 and 40 in longitudinal and transverse direction is tensile strength in MPa. Now aramid fiber reinforced polymers. Now trade name of most common aramid fiber is Kevlar and Nomex. Now chemically, this group of material is known as polyparaphenylene terephthalamide, and it is known for its toughness, impact resistance, and resistance to creep and fatigue failure. Now it has strong covalent bond axially in this direction, fiber direction. It has strong bond covalent bonding, while in transverse direction, where strong covalent bond axially and weak hydrogen bond. This hydrogen bond in transverse direction. Now it has negative coefficient of expansion due to kinks, and it has sensitivity to ultraviolet rays, so it start degrading. Now its typical application, most common application is making bulletproof vests and armors, and it is also used for making sporting goods, ropes, missile cases, replacement for asbestos in automotive brake and clutch lining and gaskets. Now, ceramic matrix composites. Now, ceramics are highly brittle in nature, thus low fracture toughness. In general, the fracture toughness is 1 to 5 for ceramics, while in case of metal alloys, it will be from 20 to 90. By making this metal ceramic matrix composite, we can increase this fracture toughness of ceramic by 6 to 20 MPa square root m meter. Now, crack initiation normally occurs within matrix phase, whereas crack propagation is hindered by the particles, fibers, and whiskers. It exhibits improved high temperature creep behavior and resistance to thermal shock. Now, brake disc of Ferrari race car, and it is made of using carbon fiber reinforced in silicon carbide matrix. Now another composite category is cermets. In this case, it is made of using ceramic and metal. So cer and mat, these initial words, they combine make cermet. Now composites of ceramic particles, strong, brittle in a ceramic particles are strong and brittle in a metal matrix, which is soft and ductile. Now it has higher toughness and wear resistance than traditional materials. And for instance, tungsten carbide or titanium carbide ceramic, they are embedded in a matrix of a metal such as cobalt or nickel. Now only about 10 to 15% of metal volume is used. So this metal, it acts as a binder phase, and they are used for cutting tools, for hardened steels, and electrical components such as resistors and vacuum tubes, valves. These are its applications. Now these are what your cermets they look like in form of tools. Carbon-carbon composite. Now both reinforcement and matrix are carbon, and these are very expensive. Now high modulus of elasticity up to 200 GPa and strength even retained at around 2000 degrees C. These are low density from 1830 kg per meter cube, and these have high thermal conductivity 100 watts per meter Kelvin, and these have low coefficient of friction in fiber direction. These also show high abrasion resistance. Applications are in making missile cone, B-2 bomber aircrafts, and wing leading edges of the space shuttle. So these all parts which are subjected to air friction, these all are made by using carbon-carbon composites. Now laminated composites. Laminate is constructed by stacking a number of laminae. So these different laminae, these are laminated together. So these can be of various types. First is unidirectional laminate. So in this case, fiber orientation angles are all same in theta will be 0 degree for all. Angle ply laminate, in this case your angles will be different and it won't be either 0 degree or 90 degree. In case of cross ply, your angles will be 0, then again 90 degree, 0, again 90 degree. In case of symmetric laminate, identical ply in material thickness and fiber orientation angle at an equal distance about a center line. So it will be at center line around that where C is distance from the mid plane of the laminate. Another composite is sandwich panels. It consists of two strong and stiff sheet faces that are separated by a core material or structure. Now it combines relatively high strengths and stiffness with low densities. Outer sheet is made of aluminium alloys, fiber reinforced plastics, titanium, steel or plywood. Core materials is rigid polymeric forms which can be phenolics, epoxy, polyurethanes. Wood will be of balsa wood or it can be honeycomb, hexagonal cells such as this. Now these sandwich panels, they have low water absorption problem, they have good anti-corrosion property, they show good thermal insulated capacity. Now this form will, because the form that we are using, it will be filled with air bubbles, so that always provides good insulation and also will reduce its density. Hybrid composites. Now, two or more different kinds of fibers in a single matrix. For example, these different type of fibers, they have certain drawbacks, certain advantages, so these all will be combined. So in case of carbon fibers, they are strong and relatively stiff and they provide a low density reinforcement but are expensive. And glass fibers, they are inexpensive and lack the stiffness of carbon. In case of the glass carbon hybrid, it will be stronger and tougher and has higher impact resistance. The fibers may all be aligned and intimately mixed with one another or laminate may be constructed. Now applications are in making baseball bat, ice skates, etc. Now there are five main techniques for making composite manufacturing. First one is hand layup technique. In this case, this is your mold. Now here first will be coating a gel coat. Now gel coat is applied to open mold to avoid sticking of polymer to the surface. Now the polymer that we are making after this won't be sticking to the mold because of this gel coat. Now reinforcement is placed in the mold. So first this reinforcement will be placed and then base resin mixed with catalyst. This container, it will be containing resin and a catalyst which will act as hardener. It will be poured into this and then brushing using this roller will be giving it shape. Now layup is made by building layer upon layer to obtain the desired thickness. Now, for an epoxy based system, the normal curing time at room temperature is 24 to 48 hours. This method is mainly suitable for thermosetting polymer based composites. Advantages is that this has low cost tools and it is versatile method. And the disadvantage is that it is time consuming, it is inconsistent and easy formation of air bubbles and disorientation of fibers. Now second method is spray layup technique. In this case, extension of the hand layup method. So it is very similar method, just we are using this spray gun. Now this spray gun, there are two outlets. So one will be for reinforcement and one will be for resin. So a spray gun is used to spray pressurized resin, and the reinforcement which is in the form of chopped fibers. So chopped fibers will be coming from this end, or then again same method is here. So this is mold, then this is a released gel coat, then we are applying some polymer and some reinforcement, then we are using roller, we are giving it shape. Now matrix material and reinforcement may be sprayed simultaneously or separately. Advantage is it is a continuous process. Any material can be used as mold and error can be corrected by respray. And disadvantages is that this is inconsistent. It has no control of fiber orientation and only one side is finished, and it is environmental unfriendly. Now pultrusion. In this case, it is made of pull and extrusion. So we are extruding one product and pulling by these fibers. So it is pull plus extrusion. It is automated process for continuous manufacturing of constant cross section profiles. In case of extrusion, we know that only cross section profiles can be formed. Profiles have high strength in the length direction. And principal reinforcement is glass, carbon and aramid fibers. So there will be around 40 to 70% of volume of these reinforcements. Now matrix materials are polyesters, vinyl esters and epoxy resins. Advantages are automated processes, high speed, it is a versatile cross-sectional shape, and it will be continuous reinforcement. Disadvantages, die can be easily messed up, and because of misalignment, if then die can get messed up, and it is expensive die. So the dies that we are required, these are expensive, and mainly thermoset matrix composites can be made using this. So now these fibers will be dipped in here. So resin impregnation. So resin will be impregnate. Now this pre-forming dye. So it will be pre-formed in form of this. Then curing dye. Here will be heating it into making our composite, and pullers, it will be giving us product. Now pre-preg. In this case, fiber reinforcements are impregnated with a specific amount of epoxy resin system in a separate step before the layup. So here this is fibers. So epoxy resin is filled in these reinforcements, and this pre-preg, it is after cutting and layup, it will be pre-formed in this shape, and then it will be performed into mold, then it will be cured, it will be heated, then it will be ejected from this die, and it will be product. In this so-called pre-pregging step, fibers are weighted uniformly and a pre-preg of high quality is formed. Now the advantages of this process is that orientation of fibers can be changed, it is consistent, and it has high productivity. And disadvantages are it is continuous process which needs more customers, It is limited shelf life. It can be subjected to delamination easily. Now, final technique is resin transfer molding. Okay, 1, 2, 3, 4, 5. Yeah, it is fifth method. So in this, it is also known as the liquid transfer molding process. So in this, dry fiber is preformed into the lower mold and the upper mold is fixed in the place. Then low viscosity resin is injected under some pressure into the mold cavity where it spreads throughout the fibers. Now its advantages is design flexibility, low startup cost, faster production and good surface finish. Disadvantages are that it has expensive tooling, it is time consuming curing and can be complex mold design is required. Now in this process here we can see that firstly we'll be using a fiber preform. So this fiber preform is set into uh, lower mold, then we'll be closing it, then inlet outlet are there, and using this pump we'll be mixing this resin and catalyst and inserting this inside this fiber preform. Now after that we'll be curing it. So after curing, for that we'll be heating, then final product will be ejected from this die, and yeah, that's resin transfer molding. Okay, now if you have any query you can ask. I'll be going through assignment questions. So because you joined late, so these are the questions. So first one was the reinforcement polymer composite is made by the incorporation of. Your options were elastomers into the polymer, fibers into the polymer, plasticizers into the polymer, or gaseous additives into the polymer. Answer was fibers into the polymer. Second question was aluminium alloys for automobile parts are reinforced to increase. Options are strength, wear resistance, elastic modulus and density. Answer was wear resistance. Third question was find the odd combination out in the following composite application. Options were CFRP, Dreamliner, GFRP, storage container, aramid, bridge reinforcement, CMC, brake disc. And answer was aramid, bridge reinforcement. Fourth question was in the Hall page model, hardness increases with a reduction in grain size because grain boundaries. Your options were act as a source of dislocation, aid dislocation motion, act as barriers to dislocation motion, or it acts as a sink for dislocations. And the answer was act as barrier to dislocation motion. Fifth question was name the process by which two or more chemically different monomers are polymerized to form a cross-link polymer together with a byproduct such as water or ammonia. Your options were addition polymerization, copolymerization, linear polymerization and condensation polymerization. Answer was condensation polymerization. Sixth question was, which of the following is a disadvantage of using polymer composites in space robotics? Options were low weight to strength ratio, susceptibility to temperature extremes, high cost of production, or limited availability of reinforcing fibers. Answer was susceptibility to temperature extremes. Seventh question, which one is not the role of reinforcement in a composite? To enhance stiffness, to enhance strength, to provide crack bridging, or to increase density? Answer was to increase density. Eighth question, what type of material is often used in the creation of soft actuators for soft robotics? So your options were shape memory alloys, carbon fiber, nylon, or aluminium. Your answer was shape memory alloys. Ninth question was, chain polymerization mechanism may occur due to cationic, anionic, only due to free radical and cationic mechanism, or all of the given options? Answer was all of the given options, because all are types of polymerization mechanisms. 10th question was, find the incorrect fact about the thermoplastics. They are soluble and fusible, they are generally linear polymers, or they are creep resistant, or they can be easily repaired. Your answer was they are creep resistant, because this is a false statement for thermoplastics. Other options are correct. So answer will be they are creep resistant. Now I'll be going through slides, so miss them. So do you have any query? Let me know. So firstly, introduction of composites, and history, natural composites that are found, why cast irons are composites, classification of composites, then various types of composites. So in that, first one is large particle composites, then dispersion strengthened composites, fiber reinforced composites, both fiber and matrix phase, stress strain curve for composites, volume and weight fractions, longitudinal modulus, transverse modulus, metal matrix composites, applications of MMCs, then polymer matrix composites in it, firstly GFRP, then carbon fiber reinforced polymers, aramid fiber reinforced polymers, then we went through ceramic matrix composites, then ceramides, carbon-carbon composite, laminated composites, sandwich panels, hybrid composites, then 5 main manufacturing techniques of composites. So first was hand layup technique, second is spray layup technique, third is pultrusion, pre-brag, then resin transfer molding. That's all. So I will upload this in the drive link that I shared with you. Okay. Guru Prasad Rao. Uh,
Thank you, madam.
okay.
Are you going to upload this, madam?
Yes, I will upload in that link I shared with you. Okay. Today I'll upload.
Okay. Thank you very much, madam.
Okay.
Very nice presentation.
Okay.
Madam,
Yes.
are you going to stop, end this session? Can we
Yeah.
leave?
Yes, you can leave. I have completed the slides. Now you can leave. If you
Okay,
have
madam.
query, you can ask. Otherwise, you can leave.
We are leaving this session, madam. Thank you
Okay.
very much.
Okay.